So hi everyone, I'm Yuhan. I'm a PhD student at University of Chicago. Today I'm really happy to talk about our work, DroidSpeak, KV cache sharing across fine-tuned model variants. And this work is a collaboration between Microsoft and U Chicago, and the majority of this work is done in my internship at Microsoft. So let's get started. So today, many LLM applications are actually powered by multiple agents, definitely, and different agents may share the same piece of long context. And by that, let's take a look at this example AI coding assistant application as an illustration. So here you can see that this user sets a very simple query, add a new feature with tests and documentations to this large code base. So this sounds like a really straightforward query, right? But let's see what actually happens. So although this is a very short query, however, the LLM inference under the hood had to prepend the short user query with a super long code, like relevant code files, and then send this as a whole to the coding agent. And before the coding agent can actually generate the new code that accomplishes the user's task, it has to process the code from scratch, and that can take tens of seconds, especially when the code has million size of code, which is really typical nowadays. But we're not done here yet. So this original code files is then concatenated with a new code sent to the testing agent, and another round of long context processing, although coding agent has processed it before. So finally, this relevant code files is then concatenated with a new text sent to the code documentation agent. And finally, another round of long context processing. So you can see that even from this very simple example, you can see that different agents have to collaborate with each other, and they have to share this, they have to repeatedly process the same piece of long context over and over again. So a very natural question you may start to wonder is that if LLM has read and processed this long context once, can it remember what it has learned? Or does it have to reread it every single time? So if the different agents are powered by the same model, then the answer is yes, with KV cache. So KV cache has been widely studied as a way to avoid recomputing the shared context within a same model. So basically, after one user queries this shared long context, then basically it goes through the long processing stage, which is also called the prefill stage in LLM inference, and it's known to be really computationally heavy. And after that, we will get this KV cache. Basically, you can think of it as like LLM's internal memory that represents its understanding of the shared context. So next time when another user comes in querying the same piece of context, then the model doesn't have to prefill the context again. Instead, it can just directly fetch the KV cache and then skip the long context repeated processing time. So you can see that KV cache is a really standard way now that lets us to avoid repeatedly processing the same piece of context across different users or different user queries, but only when they are sharing the same model. But in reality, nowadays, modern AI systems are really this simple. So there are a lot of use cases where there may be multiple LLMs coexisting in the same in a single LLM serving system. So it could be different users that they have their own personalized assistant, which are fine-tuned for their private data. It could also be different agents powered by different fine-tuned variants, fine-tuned for specific downstream tasks. Finally, nowadays in chatbots and coding assistant applications, models are periodically fine-tuned to adapt to newer data, so multiple model versions may exist in a single system. So the key question now I want to throw out today is that if there are different models that share the same piece of context, can they also share the KV cache of that shared context? So suppose we have these two LLMs, LLM A and LLM B. So if they are sharing the same piece of context, the standard approach that today's inference systems are deploying is just let A to send the raw text to B. But as we have seen earlier in the earlier example, then B has to repeatedly process the shared context again. Basically, it has to waste a lot of compute on the work they have already done before. So instead, since LLM has already done the expensive work creating its KV cache, why not just let LLM to send its KV cache to LLM B? So actually, as the first work in this direction, we limited our scope that we assume that A and B are fine-tuned variants of the same model architecture. So what does that mean is that A and B has the same KV cache shape. They have the same number of layers, tokens, and feature dimensions. So technically, yes, LLM can take the KV cache of LLM, but the real question now becomes, can LLM really understand what the KV cache of LLM means and behave as if it has computed it before? So in practice, the answer is no. So if we directly reuse another model's KV cache, that can lead to up to 60% reduction in terms of output quality compared to just sharing the original text context. So this motivates us to design a translator that can translate the KV cache of LLA to LLB. So the next question, the key question is, how should we design this translator? And actually, we've tried a lot of strawman approaches. So one of the approaches we've tried is that since this looks like a mapping problem, that we want to map LLA's KV cache to LLB's, can we train a deep neural network as a translator? But it turns out that DNNs actually can be too slow and expensive to run, and this translation operation itself can even be longer than the prefill delay if we just recompute the KV cache on LLB side. So instead of building a heavily learned translator, we actually took a step back and asked, what actually differs between the two models' KV cache? And we actually did a lot of empirical study to see the difference between KV cache of the two models. And if we compare the KV cache produced by LLM and LLM on the same piece of context for all the layers, then if we do a layer-by-layer replacement experiment, and by that I mean, for example, we can replace the first layer of LLMs with LLM's KV cache, and just let all the other layers remain unchanged. And then we feed this as a whole, this modified KV cache for LLM to do inference. And then we can get a generation quality score, which is measured by F1. The higher, the better. And so physically, we can do this for all the layers. And here in this figure, it shows the x-axis is the ID of that layer that's being replaced, and the y-axis is the F1 score maintained with that layer's KV cache replaced. And if we draw a line of the original F1 score that's obtained by using the LLM's original KV cache, then we can see that there are some layers that really has a huge drop in terms of F1 score, the generation quality. And we call these layers critical layers. And by that, that means these layers are sensitive to the KV cache difference between the two models. So in practice, we have done empirical study across eight model pairs and 6 data sets. We found that in practice, only a very small number, a very small fraction of layers are critical layers. And in practice, that's 11% across all the data set and model pair on average. So this gives us a first key insight in DroidSpeak's translation algorithm. That is, only the critical layers are sensitive to KV cache difference between the two LLMs. And this motivates us to only recompute the KV cache for the critical layers, while we can reuse a KV cache for the other layers. So to make this practical, another remaining question to be answered is, how can we determine the critical layers? And one option definitely is to do this layer replacement experiment online for every new data, but that will be too expensive to run online. Instead, we ask the key question, are the critical layers input specific, or do they somehow remain consistent across different inputs? And to answer this, we take multiple different contexts and run both LLM and LLM on each of them. And for every context, we compare their KV cache layer by layer, and we compute this per layer difference as we normalize the KV cache difference and make that a single score for each layer. And that's basically this figure. And if we do that for all different kinds of contexts, what we find is that although the absolute KV cache difference is different for different inputs, but the key is that the critical layers actually remain consistent for all inputs. So this is very important and helpful because this can allow us to identify the critical layers offline with a profiling dataset for each model pair, and then reuse this critical layer set during online inference. So now that we know that we only want to recompute part of the layers in KV cache, so how does this actually work? So on the left-hand side, this shows the standard full recomputation approach, where LLM basically takes the raw text context, runs through the full prefill across all the layers, and then we get a fully recomputed KV cache. And for DroidSpeak's partial recomputation, let's assume that the third and the fourth layer are the critical layers. So for the first two layers, we just simply reuse LLM-A's KV cache. We just directly fetch from LLM-A. So the key challenge here is that the transformer layers are sequential. So if we want to recompute any layer, we actually need the hidden states flowing into that layer. However, if we simply reuse the first two layers KV cache, we're actually losing the hidden states flowing into the third layer. So to address this, DroidSpeak also transits the hidden states from LLM-A, and we start recomputing from this third layer's hidden states from LLM-A. So the final KV cache is a hybrid cache. It contains the reused KV cache and recomputed KV cache. So this can help us to save prefill computation while maintaining quality. So far I've been describing what DroidSpeak recomputes, basically only the critical layers. And then the next question is, when should this recomputation happen? So a very naive design would be like transferring LLM-A's KV cache across the network first, and then only start recomputing afterwards. But an interesting and key system level insight in our paper is that we find like the recomputing can happen as long as the hidden states of the transitioning layer from reuse to recompute arrives on LLM-B side. So basically, we're pipelining the transferring of the non-critical layers KV cache from A to B, and then we first transit this hidden state of the transitioning layer, starts recomputing, and pipeline this delay. So as we can see in later results in evaluation, it's especially valuable when internode connection is limited. So just a very high-level view of how DroidSpeak does overall. So given this pair of model A and B, we first go through DroidSpeak's offline profiler to determine the set of critical layers to recompute for this model pair. And then during the online inference stage, assume that LLM-A first consumes this context, this super long context, creates its KV cache, and then LLM-A splits this KV cache into many layers, goes through DroidSpeak translator online, where it basically reuses the KV cache for non-critical layers while recompute the critical layers KV cache. So finally, this combination of reuse and recomputed KV cache is then sent to LLM-B for inference. So now let's see how this performs. So our evaluation setup uses two fine-tuned variants from the same model family, and each model is served on a dedicated 8A100 Azure node, and each model is replicated across these 8 A100 GPUs within each node, and any incoming requests are dispatched to one of the GPU per node in a round-robin fashion. So these two nodes are connected with a network link with 17 gigabytes per second. And the workload is multi-hop question answering from HopQA, which is a very popular long context question answering dataset. And then the first model prefills the context and the KV cache to another node. So the first question we want to understand is how's the quality and latency trade-off. So on the axis here, it shows a prefill delay in seconds. And for DroidSpeak, that includes a transmission delay and recomputation delay. And on the y-axis, it shows the F1 score, which is the higher, the better the quality is. So we compare DroidSpeak with re-computation baseline, which basically let A to send the raw text to B, and then B does the re-computation. And we also compare with direct KV cache reuse, which directly reuse the first model's KV cache. So you can see here, this is where DroidSpeak is. You can see that DroidSpeak can greatly reduce the prefill latency while maintaining the generation quality. And similarly, this can translate to inference throughput improvement. So here on the x-axis, this shows the query per second, which basically measures the inference throughput, and y-axis shows the prefill delay. So this is where the recomputation baseline is, and this is DroidSpeak. We can see DroidSpeak can have like 4x inference throughput improvement. So just to quickly conclude this talk, so the motivation of our work is that different LLMs could share the same piece of context, but no one has studied how KV cache can be directly shared across different LLMs before. So DroidSpeak is the first system that is designed to translate the KV cache across different fine-tuned model variants. And the insight we use, a key insight is that only a small subset of layers really matters in terms of the KV cache difference. And our solution is to only recompute those critical layers while reuse other layers KV cache. With that, I'm happy to take any questions, and thanks everyone for listening.